In this video, we will be learning about circuits, Ohm's law, transformers, magnetic field, and magnetic flux. To start off, we need to learn what Ohm's law is. Ohm's law states that the current I is equal to voltage over resistance, where I is measured in amps, denoted by capital A, V measured in volts, denoted by capital V, and resistance measured in ohms, denoted by this half circle symbol you see here. Now, when we see a circuit, if you look at the bottom left of your screen, you generally will see 2 to 4 lines. That denotes the battery. The longer side is the positive side, the shorter side is the negative side, and generally when a current runs through a circuit, through the wire, it runs from positive to negative. So in other words, looking at this circuit, the current is running this way. Now these little spikes that we see right here, those are our resistors. Resistors work to restrict the flow of current. So what exactly is current? Current is a bunch of tiny charged particles all moving within the same direction. So a good analogy that I've come up with to help you wrap your mind around things is a roller coaster. So when you think of a roller coaster, you think that you have a track, which we can make analogous to the wire, and the battery, which is where the the current comes from. The battery produces a voltage. Voltage is kind of what pushes the current through the wire. So we'll make the analogy that the carts on the roller coaster is the voltage carrying the people. Each individual person is an individual particle, charged particle, running through the track or through the wire. And if you've ever been on a roller coaster, you know that after you make a big drop, there's usually some brakes, so we'll call the resistors the brakes. Okay? An important relationship to understand when dealing with Ohm's law is that as the current I increases, velocity increases, but resistance will decrease. And vice versa for all the other directions. The resistance should be increasing, Okay, so if we were to take the circuit that we were given on the left, this is a little bit of a simpler version of it. So if we were to look at the circuit, and we would suggest that the current is already running through it, it would produce a magnetic field. A magnetic field is a region around a magnetic material or a moving electric charge within which the force of magnetism acts. So if we were to relate it to our analogy, we could say that person 1 standing here and person 2 standing here. Now as the roller coaster travels down, person 1 is going to feel a gust of wind. Person 2, however, will not, because they are not close enough. So the area or the vicinity that you have to be within to be able to feel the gust of wind from the roller coaster can be analogous to your magnetic field. So magnetic field's an area that you have to be within to feel the effect of something. It is usually related to as the B field. So B field and magnetic field can be used interchangeably. It is measured in Teslas, denoted by capital T that we see right here. And when we are denoting that there is a magnetic field on the page, we'll use either X's or dots. The X's mean that the B field is going into the page. The dots or O's mean that the B field is coming out of the page, because remember, it's an area, not a plane. So a way to keep track of the direction of the B field and relevance to the current, as well as the overall force they produce, is the right-hand rule. So if you look at this picture in the red box right here, you will see that your thumb is supposed to represent the direction of the current, your fingertips the direction of the B field, and your palm the direction of the overall force. So if we were to give the current that we drew over here a B field, and we were to look at the left side of the current where the battery is, you would point your fingers towards the screen because it's X's, so the B field's going in, or it's behind the page, the area is behind the page. On the left side, the current is traveling up from the battery, so your thumb should be pointing up. Therefore, your force should be to your left. And if you follow the current with your thumb, it turns right. So your thumb should now be facing right with your fingertips still pointing at the screen. At the top, you will notice that your force is now up because your palm is facing upwards. And if you follow the current around, you will see that each side has a different force because the current is traveling. Now all of these forces cancel out, so in a uniform magnetic B field, there is no net force because they tend to cancel out. Okay, so flux is the measurement of magnetic field passing through an area. So in other words, how much wind is passing through a specific area. Flux, a couple things to know is that flux is proportional to the density of flow. Flux varies by the boundaries facing the direction flow, and flux is proportional to the area within the boundary. So if we were to look at, say, this part up here versus this part down here, these two would have very different amounts of wind associated with them, right? So the first stop would have maybe a little bit of wind, not so much. The second part, however, would have a lot of wind because of the velocity. So that's what the first part is saying, is that flux is proportional to the density of flow. Now, if, say, the roller coaster was stuck at position 1 and a big strong gust of wind passed by, the carts would tend to move a little bit. This is kind of how the idea of changing the magnetic field, or analogous to the amount of wind, creates a voltage, because it would create a voltage of movement, and then the current would be start being pushed through the wire again, or in this case, the carts would start pushing the people along the track again. So therefore, a change in magnetic field, a change in the wind, creates an induced voltage. An induced voltage is an electrical potential created by an electrical field, magnetic field, or current. So the equation for induced voltage to figure out how much voltage is caused by the change in magnetic field is Faraday's law. Faraday's law states that E, the electromagnetic field, the induced voltage, is equal to N, the number of turns, which we'll get to what that variable means in a second, times the change in flux, the change in the B field, over the change in time. So when we think of the symbol up here, the change in flux, how exactly do you measure the change in flux? The change in flux, if you look right here, is defined as the magnitude of the B field times the area you're looking at and the angle between them, or the angle between the B field and the regular plane. So as you see in this diagram below, the B field is going straight up. The area, however, is at an angle, theta. If the area of the plane of the area that you were looking for were to be down on this blue sheet, it would be flat. They would create a 90-degree angle, with this being the area and the arrows going up being the B field. However, in most cases and in most of the problems, when the angle is 90, you would take cosine of 90, and cosine of 90, or you would take cosine of 0, because the angle would then be flattened and create no angle. So the cosine of 0 is equal to 1. So in most cases, you won't even see this last part in the equation. You'll just see magnitude of the B field times the area. So how does all of these concepts relate to transformers? So on the left side of your screen, you'll see a picture of what an actual transformer looks like. You may have seen them around your neighborhood. And over here is kind of the insides, how the transformer works, right? So a transformer is a passive electrical device that transfers electrical energy from one circuit to another, or multiple circuits. So when it says from one circuit to another, it means from the primary coil to the secondary coil. And since we know that the rate that the power is supplied to both of the coils is the same, we know that the variables involved in them, they produce ratios, right? So each coil has its own induced magnetic field when the flux is changing for each of them. However, these values give us ratios that we see right here, where, remember, V is, in this instance, V is voltage, Remember that variable from Ohm's law. I is current, also from Ohm's law. We just learned about induced voltage, which is this little e that you see. And then we talked a little bit about N. So N is the number of turns in the coil. So you see in the picture over here, the primary coil's N in 1 is more than in 2 because there is less turns in their coils. So let's try to apply these ideas to a problem. So the problem states that a soldering iron uses an electric current in a wire to heat the tip. A transformer with 100 turns on the secondary coil provides 50 watts at an RMS voltage of 24 volts. So first with these problems, I like to start out with a picture to get an idea of what I'm looking at. So now we have our picture. We can start with part A, where it asks, what is the resistance of the wire in the iron? Now, as mentioned before, the rate of power supplied to both coils is the same. Therefore, with the given variables, we cannot use Ohm's law because we have no idea of any current. However, we can use this new equation that you see here in the blue box, because since the power is the same for both coils, we are given the power 50, and we would just plug in the voltage and resistance for the specific coil that we're looking at. So in this case, we would use our given variables. Power is 50 watts is equal to voltage squared, so we were given 24 volts, over R, which is what we're solving for. If we were to rearrange this, we would have 24 over 50 for R, and that would give us a value of, 24 squared. Important to pay attention to those equations. So 24 squared over 50, which would give us 11.52 ohms. However, taking into account significant figures, we would round up to 12 ohms as our final answer. So now we can add that to our knowns. So for part B, it asks, how many turns are in the primary coil? So since we have more than 2 variables for our secondary coil, and we know that the voltage for a regular socket outlet is 110 volts, so we will use that as the voltage for coil 1. Therefore, we are choosing to use this formula. So we will plug in our values over here. And now we will solve for N1, and we get that N1 has, or the number of turns for the primary coil is 458, but if we were to round due to significant figures, we will get 460. So the last question we are asked in part C is, what is the current in the primary coil? We can then use our one last ratio, is that the current in each of them is proportionate to the amount of turns in each of them. Now you may be noticing we're missing 2 variables. However, using Ohm's law, it is possible to solve for the current in the secondary coil because we have both the voltage and resistance for it. We plug that into Ohm's law, V over R. We get that the current in the secondary coil is 2 amps, so we will plug that into our ratio and solve for I1. And we get that the current in the primary coil is 0.43 amps. So we're going to clear up some space and write out all of our answers clearly. And those are our answers to A, B, and C.